So hi everyone, my name is Dr.Petibon and I'm an instructor in the Gordon Center at MGH. And today I'm going to give the first lecture in a series of 2 lectures on positron emission tomography, or PET. So the goal of today's lecture is really to cover the basics of what this imaging modality is about. And in the next lecture that will be given by Dr. El Fakhri on Thursday, I think he'll go more into the details of the instrumentation, data acquisition, data correction, etc. So the goal of today is really to provide a broad overview so that you can understand next Thursday's lecture, basically. So this is my email address. So if you have any question after the class, please feel free to reach out. And also, please don't hesitate to interrupt during the lecture to ask questions if you have any, okay? So, so we're gonna get started. What is PET? So PET is an imaging technique that belongs to the family of nuclear medicine imaging methods. So nuclear medicine imaging, as you might know, is a medical specialty that focuses on evaluating physiology and tissue metabolism in vivo using tracer techniques, okay? So to obtain an image in nuclear medicine imaging, you need to administer radioactive molecules to your patient, also known as a radiotracer, that is formed by attaching a short-lived radionuclide that's going to emit some radiation that the camera can detect, to which a biologically relevant compound has been attached, okay? So you use that radionuclide to basically image the function that the molecule here that has a specific biological interaction with the organs is going to allow you to image, okay? So it's really important to emphasize that unlike many of the imaging modalities that are used in the clinic, such as X-ray, computed tomography, or MRI, nuclear medicine imaging really focuses on analyzing the function of tissue and organs rather than their anatomical structure. So I think you can have a sense about the difference between functional imaging and anatomical imaging by just looking at the pictures that you get from these scanners. So this is a CT image here. So taken from the upper thigh to the skull, basically showing you very high detailed anatomic information, highly detailed anatomic information. So you see the lungs here, see the liver, the heart, skull, the brain, and with a very good spatial resolution. MRI similar, although it provides, it uses a very different contrast mechanism, but still you can see very detailed anatomic information. So look at the brain, for instance, much more detailed than what CT is providing, because you can see, for instance, differences between gray and white matter, but overall you see, of course, this is anatomic information that you're getting. So compare that now to what PETs can provide you. So this is a PET scan that was done using the radiotracer F18 fluoride. So this measures bone metabolism. So as you can see in your scan here, you only have signal coming from the bones of the patients, okay? You do not see the liver, do not see the heart or the brain, you just see bones, because that's what your tracer is targeting, okay? So why we are using that? For instance, if you look at this image here, you can see that there are some areas of increased uptake of F18 fluoride in the bones of this patient, and that would typically indicate bone cancer, okay? Unfortunately for these patients. Compare that also to another PET image that was obtained using FDG. So FDG is targeting a very different function. It's targeting glucose metabolism. So here you're basically visualizing the glucose consumption of organs in this patient. So you see the brain that lights up a lot. But very different information from the one that you get from F18 fluoride or from CT and MRI, okay? So it's just to give a quick introduction on anatomic versus functional imaging. So now I think we can go further into explaining what PET is about. So positron emission tomography, or PET, is the second major method for tomographic imaging in nuclear medicine, the other one being SPECT, so single photon emission computed tomography. So SPECT to this day is still more widely used than PET, primarily because it's cheaper. But PET, the importance of PET is increasing every year in the clinic, okay? So this is a short definition of PET that actually encapsulates many of the concepts that we're going to talk about today. So PET consists in the coincidence detection of annihilation photons that are indirectly emitted after decay of positron-emitting radioisotopes that have been administered to the patient, followed by the reconstruction of the activity distribution. So it's a very dense definition, but I think it contains many of the things that we're going to talk about today. And I've underlined 3 of them. So coincidence detection, annihilation photons, positron-emitting radioisotopes. So reconstruction, we're not going to talk about that today because you're going to have a dedicated lecture on reconstruction later this fall. So really those 3 first concepts that we're going to explain today, okay? So these are some unique features and advantages of PET over SPECT. So first of all, PET uses what we call electronic collimation instead of lead collimation. So as you may remember, in SPECT, in order to obtain spatial information on the signal, you would have to place those heavy collimators in front of the scintillators, okay? In PET, we do not have any type of lead collimation. We use electronic collimation that is also called coincidence detection, okay? So obviously, a big gain that you're gonna get by not having lead collimators in PET is a huge increase in terms of sensitivity because, collimators are blocking many of the photons that are emitted from the patient. So PET has a much higher detection efficiency as compared to SPECT. So typically 2 to 3 orders of magnitude more photons detected during a PET scan than a typical SPECT scan, okay? So to give you an idea, in SPECT, you detect approximately 0.01% of the photons that are emitted from your patients. In PETs, that goes to between 1 and 2% for whole body scanners. So it's a big gain that we have in terms of sensitivity. And of course, sensitivity is very good to have because that means that you're going to have a higher signal to noise ratio in your image. So the images are going to have higher quality. And also you can reduce the radiation exposure of the patient because you can administer fewer radioactivity for PET as compared to SPECT, okay? A very important feature also is that PET provides a more uniform spatial resolution than SPECT. So as you may recall, in SPECT, the spatial resolution is very much dependent on the distance from the source to the collimator. So because we do not have collimators in PET, we do not have this type of effects. So it's the spatial resolution of the images are much more uniform. So they are not fully uniform, as we'll see later, but they're more uniform, and that's clearly an advantage, okay? Because you can image the patient's organs with pretty much the same accuracy, basically. Very important thing also of PET is that feature of PET is that it provides absolute quantification of activity, okay? So if you are looking at a PET image, the actual values of the pixel that you're looking at contains an estimate of the concentration of activity in that pixel, basically. So in becquerel per milliliter of tissue. And that is a pretty accurate measurement, actually. That is much more difficult to do in SPECT for a number of reasons. One of the principal one being the difficulty to do attenuation correction in SPECT, I believe. So that is really important. So PET is really quantitative. And finally, PET tends to use shorter lived radioisotopes as compared to SPECT, okay? So in SPECT, for instance, technetium-99 has a half-life of about 6 hours. So here in PET, we use those types of isotopes here whose half-lives are ranging between a few minutes to up to 2 hours. So why is that an advantage? 2 things. First of all, as you know, radiation exposure is a function, of course, of the amount of activity that you're giving to your patient, but also the time during which those isotopes are emitting radiation. So shorter lived radioisotopes means that you're going to have lower radiation exposure. And of course, because your isotopes decay faster, you're going to have more photons emitted per unit of time if you have shorter half-lives. Okay, so that's I think an important one too. Do you have any question on this before we move on? Okay, so we're gonna anyway come back to all this throughout this lecture. Okay. So before talking about PETs in more details, let's quickly recap how SPECT was working. So as you may remember in SPECT, of course, you have to administer radioactive molecules to the patient, and during decay of those radionuclides, you would have a gamma photon that would be emitted, okay? So for instance, for technetium-99, the gamma photon here that is emitted has an energy of about 140 keV. And you have your panel of scintillators and collimators here that are used to detect those photons. So the collimator here is blocking basically all the photons that do not have a specific trajectory. So that's, you basically have special information associated to your photons that you're detecting, okay? So this is how SPECT is working. Now for PET, you know, we're using a very different type of radioactive nucleus. These are so nucleus whose most probable form of decay is by emitting a positron. Okay, so that they typically have one extra proton inside their nucleus as compared to the stable form. Okay, so those are produced artificially; they cannot be found in nature, as we'll see later. But during decay of that radionuclide, the extra proton that is there is going to convert to a neutron, and then you're going to have two particles that are emitted. One is a neutrino, but we don't really care about the neutrino in PET. What we really care about is the other particle that has been emitted, and that is a positron, okay? So I guess you all know what a positron is? Yeah. So a positron is an electron with a positive charge. So it's the antiparticle of the electron, okay? So recall that you have a proton that has a positive charge, becomes a neutron, so neutral charge, and then the charge is carried away in the positron, okay? So what's going to happen is that the positron is going to travel a little bit in the matter, and eventually is going to encounter an electron. And what happens when the positron and electron meet? They are going to undergo what we call an annihilation reaction. So they're going to combine and then release their energy in the form of two gamma photons that are emitted at approximately 180 degrees from one another. So they are anti-collinear. And each one of those photons here has an energy of 511 keV. So you can find this quantity here by just putting the mass of the electron here times the square velocity, and you'll find 511 keV. So each one of those photons has a 511 keV energy. And the goal of the PET scanner is going to detect those two photons, okay? So in PET, you know, because you do not have collimators, you really need to detect the two photons. So you need to detect a pair of gamma photons, because if you detect a pair, then you know that the site of annihilation is somewhere between the two detectors, and that's how your signal is collimated, basically, okay? So a huge component of the PET scanner is going to be to process those photons and assign them to pairs, basically. So look at the timing information for those photons, and you know, to decide whether they form a pair, they are likely to form a pair or not, okay? So that's how the signal is collimated in PET, okay? So these are some commonly used positron-emitting radionuclides. So I've listed a few here: carbon-11, O15, fluorine-18, rubidium, gallium-68. This is a half-life of these radionuclides. So this is the time, of course, it takes for half of the radioactivity to decay. This is a branching ratio here for positron emission. So this is a percentage of decays that are done by emitting positrons. So of course we want a high branching ratio. And this is a production method. So as I was saying, those isotopes cannot be found in nature. They have to be artificially produced. And the main method to produce them is by using a cyclotron, okay? So a cyclotron, as you may know, is a particle accelerator. So it's a very expensive device to have in a hospital and to maintain. So typically what's going to happen is that many hospitals that have PET scanners do not necessarily have cyclotrons, and therefore they are going to have to receive you know, those radionuclides from other sites that are equipped with cyclotron, okay? So if you look at the half-lives here, for instance, if you're talking about carbon-11 or 15, you're not going to be able to do those studies if you do not have a cyclotron on site. So, however, for fluorine-18, with a 2 hours half-life, you can, you know, typically produce it somewhere in one hospital and then distribute it around. So that's going to be the most important radionuclide in PET, so fluorine-18, because it's, you know, it's so convenient to have a 2 hours half-life, okay? And it's, of course, produced with a cyclotron. So let's quickly talk about how cyclotrons works without going too much into the details. So these are the reactions that are occurring within a cyclotron. So to produce F18, you have a target of O18. You smash the target with a proton, a neutron is emitted, and then you're going to have fluorine 18, okay? So same thing for carbon 11 with a different target, and that's how you, so you send a proton on the target of ammonia, then you have alpha particle emitted and you get carbon 11. So now, of course, in order for the proton to interact with the nucleus of the target, you need to confer a certain energy, and that energy, of course, has to be higher than what we call the nuclear binding energy. So that's the energy that, making the nucleus not explode, basically, because you have protons there that have positive charges, and if there wasn't this force, then they would just like the nucleus would implode. So you have to overcome this force there. And so this is a graph here showing the binding energy for different atoms here as a function of the number of nucleons in the nucleus. You can see that for oxygen, for instance, you need to have at least 8 mega electron volts to overcome the nuclear binding energy. So in order for this reaction to happen, so at least 8 mega electron volts. So how is the cyclotron doing this? So this is a top view of a cyclotron. So this, it has multiple components to it. So one is a magnet. So it's producing basically a magnetic field that is perpendicular to the slide, okay? Then you have some electrodes here that are called Ds, because they have, they look like a D, basically. Then you have your target that is placed here, your source of ions that's going to place here. So typically we use, for F18, we use the negative ion of hydrogen. And then to send your charged particles here, from here to here, with enough energy, basically the cyclotron is going to apply a very high alternating voltage between the electrodes so that it can successively, attract and repel those charged particles. When you apply a positive charge, you're going to attract the hydrogen anion, and when you apply a negative charge, you're going to repel it, basically. And with the action of the magnetic field, you're going to confer a spiral trajectory to those particles so that overall, in the end, they will reach enough energy so that they will hit the target and then produce the reaction that we want, okay? So that's, I'm not an expert in cyclotrons, so I think you'll have a lecture on radiopharmacy later on, so probably you'll talk more about that. But this is just roughly how it works. So of course, as I was saying in the beginning, it's not only the radionuclide that you're injecting, the positron emitter is the radio tracer. So it's a molecule that is composed of a biologically relevant compound that you're interested in imaging, to which one of those radionuclides has been attached so that you can measure it with your PET camera. So a very good example of radio tracer in PET is the radio tracer FDG. So it accounts for more than 95% of all the PET scans done in the clinic. So it's a very, very important one. And what is it about? It's basically a glucose analog that has been labeled with F18. So at the bottom here, you can see the glucose molecule on the left and the FDG molecule on the right. So you can see that the only difference here is that they have placed an F18 here in lieu of the OH group here. And that's basically what you're going to see. That is a marker for glucose metabolism. So it allows you to image glucose metabolism in the patient's body, okay? And I'm sure you know why we're so interested in measuring this. It's because cancer cells actually have higher metabolic demands than healthy cells. So they're going to take up much more FDG than healthy tissue, and that's how we're going to be able to detect tumors in someone's body, basically, okay? So this is an example here of FDG PET scan. So it's a whole body PET scan. So you can see all the major organs that have a lot of, energy demands, such as the brain, the heart, the bone marrow here, relatively little. This is just the bladder. So this is, the FDG secreted out of the body via the bladder. That's why it's showing up so much. And that's why we usually ask the patients to go to the restroom before they are scanned with PET, because we don't want this structure here to obscure other potentially malignant findings. You can see also the muscles here. So this patient actually has a little bit too much muscle uptake than we'd like. So typically we ask patients to be at rest before they're injected with FDG, because we don't want the muscles to take up too much FDG, so that it will hide other other lesions basically. But overall, this is a normal FDG scan, so nothing to worry about here. And on the right, this is another one. So for another patient, you can see again the major organs such as the brain, the bone marrow, the bladder. But what you can also see in this picture are those areas. So these are spherical areas of increased FDG uptake that are located in the patient's thorax. And that is typically not something you would expect in someone without disease, and that would typically represent potentially a tumor. Okay, so that's how we would pick up, potentially, cancer on these patients by looking at abnormality in the distribution of FDG. Okay, these are the kidneys here, so this is completely normal. But there is something here that also you can see, I guess, that is located in the arm of the patient. And that is, it's not a tumor. This is actually something that can happen when the injection of FDG that is done, in the arm, hasn't worked well, and then you have FDG that is under the skin, basically. That makes a big area of uptake. But of course, people who interpret those scans know that, and they will not think that this is a lesion. Okay. So of course there are hundreds, if not thousands of tracers, but I'd like to talk about one that is used in brain studies, and that is an important one in research especially. So it's called C11 raclopride. So this is the raclopride molecule. So it's an antagonist for dopamine receptors in the brain. So this was actually a drug that was developed to treat, I think, schizophrenia. And it basically is going to bind and block the dopamine D3 receptors. And this is the PET tracer that was developed based on this molecule. So you can see that the only difference here is that you have a carbon 11 in place in lieu of the, instead of the carbon 12, basically. And that's how you're going to be able to image that with your PET camera. And this is the type of image that you get with raclopride. So compare that to an MRI image. So MRI, very high definition, a very high resolution anatomy of the patient. So all the gray matter, all the brain structures here. And this is the raclopride PET image. So you see on this signal, most of the signal is going to, to be located in the area that has the most D2, D3 receptors. So that is typically the striatum. So it's this M structure that we see here in the raclopride PET scan. So it's specifically binding to those receptors, and of course, healthy, there are some diseases where you have a lower amount of those detectors, and as compared to healthy people, and that's how this tracer is used, not clinically, but in research, especially to look at those diseases. Okay. So do you have any question on this before we move on all the slides that we've seen? No. Okay, so before talking about instrumentation, etc., for PET, I'd like to quickly recap the different types of interactions that can occur between the annihilation photons and the matter through which they are traveling. So this is a graph here that's summarizing what's going on. So this is showing you basically the dominant type of interactions between photons and matter as a function of the energy of those photons and the atomic number of the material through which they are traveling. So you can see that, as we said, annihilation photons have a 511 keV energy. And here, so if you look at lower density materials, such as human tissue, so a Z between 8 and 20, so 8 for soft tissue, 810 for soft tissue, 20 for bones, basically. The Compton effect is going to be the dominant type of interaction between photons and human tissue, okay? Now, if you look at the detectors that we use in PETs, so these are scintillation detectors, so they have a very high Z, and that's done on purpose. Here you can see that it's a combination of Compton and photoelectric interaction, okay? So this is done on purpose. We want to maximize actually the probability of photoelectric effect in detectors. because we'd like photons to, when they interact with a detector, to deposit all of their energy in that detector and be detected, basically. So that's why we have to use high Z material to maximize the probability of photoelectric interaction, okay? So quickly, let's review Compton and photoelectric interactions. So this is Compton. So it's called also Compton scattering. So it's basically a collision between a photon and a loosely bound electron, typically from the outer shell of the electronic shell. So what's going to happen during Compton interaction is that the photon here is going to transfer some of its energy to the electron, and then it's going the photon's trajectory is going to be deflected through some scattering angle theta, okay? And eventually, if the energy transferred to the electron is higher than the binding energy of that electron, you're going to have a recoil electron that is going to be emitted, okay? So as you can imagine, Compton scattering is not something that we'd like to have in PETs because, if you had your annihilation here, you have the photon that is emitted. After scattering, this is what you're going to detect, okay? So the trajectory of this photon is actually not going through the site of annihilation, which is somewhere here, and therefore it's going to carry erroneous spatial information. So typically we are going to try to correct for scattering in PETs as much as possible because we don't want those photons to contribute to our signal. So not so good Compton scattering. We want to get rid of those. And you'll see that with George on Thursday's lecture, how we correct for scatters. Photoelectric effects. So again, the dominant type in the scintillators. So this is a collision again between a photon and an electron, but this time typically from an electron that is located in the inner shell of the electronic shell, okay? And during photoelectric interaction, the electron is going to absorb all the energy of the photon, okay? And if the energy that is absorbed is higher than the binding energy of that electron, a photoelectron is going to be emitted, okay? So, of course, as I was saying before, this is what we'd like to have in our detectors because we want the scintillators to absorb the gamma photons so that they can be detected. We don't want them to scatter in the detector and then go to some other detector and be detected there. We really want to maximize the probability of photoelectric effects. If photoelectric effect occurs inside the patient, which can happen because after the photon has scattered, it can be absorbed because it has lost enough energy. You're never going to detect those photons, so that's going to lead to a loss of signal, okay? But we have to live with that. So, so these are Compton and photoelectric interaction. Now we can talk about some basics of instrumentation for PET. So, of course, in order to obtain a PET image, you need a PET scanner. So what is a PET scanner? It's actually made of several rings of scintillation detectors that are placed around the patient. So there's a very different geometry than SPECT, okay? You have a full ring of detectors here that is surrounding the patient, and typically you have multiple of them that are stacked against each other, okay? So this is a transactional view of your scanner and your patient. So you will have multiple rings that are stacked, perpendicular to this slide, basically. So each one of these rings contain hundreds of scintillation detectors that have two parts. So one part is a scintillator. So this is a crystal that is used to convert those high energy gamma photon into thousands of light photons. So these are the scintillation crystal. And then you have another component here that is called a photodetector. So this is going to be used to convert those light photons into electricity and amplify that electric signal so that we can work with it, okay? Of course, as I was talking about in the introduction, a very important component of the PET scanner is going to detect pairs of gamma photons. That is what we call coincidence, okay? So two gamma photons must be detected at approximately the same time if they are likely to come from the same annihilation, okay? So very important component of the PET scanner is going to be to decide whether gamma photons actually, form pairs of photons. And that's what will constitute your valid data in PET. So pairs of gamma photons. That's called the coincidence processing unit, okay? So this is an overview. This is a an example of PET scanner that we're still using at MGH. So this is kind of an old model. So this is the HR Plus. So I think it was commercialized was first commercialized in the end of the 80s and early 90s. So it's a pretty old scanner, but we're still using it, although it's close to retirement. So it has 32 rings of detectors that allow you to cover approximately 16 centimeters worth of your patient. So if you want to do a whole body scan, you have to do 6 to 8 different acquisitions to cover each part of the body, basically. So each one of those rings has 576 detectors, leading to more than 18,000 detectors total. Okay, so the bore diameter here is 82 centimeters. So it's a pretty large bore. This is another type of PET scanner that we're using, especially in research. So this is actually not simply a PET scanner. This is a simultaneous PET-MR scanner. So it's a much more recent technology. So it was commercialized in the early 2010. And it actually allows you to acquire simultaneously the MRI images and the PET images. So you actually have a PET scanner here that is inserted within a 3 Tesla magnet, okay? So it's a pretty, you can imagine the engineering that was necessary to achieve that, to have a fully functioning PET scanner inside a 3 Tesla magnetic field. It's a pretty impressive machine. So it has 64 rings, a total of 32,000 detectors. And the field of view here is longer than the HR Plus. So it's about 26 centimeters. So it's better. You're going to detect more photons, and also you can do those whole body exams faster because you require fewer bed positions. The only problem that we have with this scanner, and that is actually, sometimes a little bit of a pain sometimes, is that it has a pretty small bore diameter, so only 65 centimeters, because there are physical constraints for fitting a PET scanner inside an MRI scanner. And that will mean that, first of all, you shouldn't be very claustrophobic to get in. And also, typically, larger patients we're not going to be able to scan larger patients. So typically above BMI of 32, I think we're not allowed to scan, at least in the research setting, to avoid, unwanted consequence events, basically. So yeah, that's the MMR. And that's it for that. And now let's talk more about the basically the detectors that are used in those scanners. So it has 2 components, as I was saying. So one is a scintillation crystal. So the role of the scintillation crystal is to stop those incoming high energy annihilation photons, so 511 keV. And in doing so is to produce a flash of visible light, okay? So you're going to have those high energy photons here that are going to interact with the crystal via, via photoelectric or Compton interaction. So as we've seen before, all those interactions are going to lead to electrons that are going to be, emitted. Those electrons are going to collide with other electrons of the crystal, exciting those electrons. And then when those electrons go back to their lower energy state, they are going to release their energy in the form of light photons. So typically a few electron volts each. So that corresponds to blue light, okay? So high energy gamma photon becomes thousands of light photons in the scintillation crystal. So the second part of the detector is what we call the photodetector. So the role of the photodetector is twofold. Is to convert light photons into electricity and then amplify that electric signal, okay? So a very good example of a photodetector that was used until relatively recently in our PET scanners was the photomultiplier tube, or PMT. So I think nowadays modern PET scanners use other types of technology such as avalanche photodiodes or silicon PMs. But I think it's still important to know what a PMT is doing, because it has been so important in the field. So it has different components. So one is a photocathode here. Then you have diodes that have an increasing voltage that are placed inside an evacuated glass tube. And you have the anodes here. So this is the output. So now you have light photons that are coming from the scintillation crystal that are going to interact with the photocathode, creating one photoelectron, basically. And this photoelectron is then going to be guided towards the diodes and amplified based on the increasing voltage that is applied to the diodes. So that between the anode and the photocathode, you have a gain of about 1 million to 10 million. Okay, so it's a pretty high gain, and that's why PMTs have been used, for so long in PET imaging. Okay, so it's a pretty good amplification factor. So to summarize, this is the synthesis detector. So high energy gamma photon becomes thousands of light photons. Light photons are transmitted to the PMT that is going to produce a measurable electric signal. And what I'm saying here is that usually the amplitude of this electric signal is proportional to the energy deposited by the photon in the crystal, okay? So energy information is actually very important in PET because, as you may recall from the introduction slides or the slides before, there's going to be a lot of compton scattering going on inside the patient. So those photons, as we've seen, are going to lose some of their energy. And basically a first, rough correction for scatter that the PET scanner is going to do is to basically threshold the energy so that you reject all the photons that have an energy that is, below 450 keV, for instance. Because if they hit your crystal with 450 keV, they are very likely to have scattered in the patient, and therefore you don't want those to contaminate your data. Okay, so first. The first way to do scatter correction is to actually threshold energy so that you only accept a certain energy level, okay? So any question on this? No? Okay, so a very important component of the PET scanner is, as I was talking about before, is the coincidence detection unit. So that is, the unit that is going to decide whether two gamma photons are forming a pair of photons and whether they constitute a coincidence event, basically. So an important component of that is to, of course, perform time pickoff. So assign a timing event information to each detected photon. So typically the electrical pulses that have been generated by the PMTs are passed to what we call a constant fraction discriminator, a CFD, that will generate a timing signal for each pulse, okay? So this is very simple. So you have annihilation here, two gamma photons are emitted, you have two detectors here, and then you're going to have two electric signals that are corresponding to those gamma photons outputted by the PMT, basically. So those are passed to the CFD, and what a CFD is going to do, as its name indicates, is going to assign a timing information to each photon whenever the signal here has reached a constant fraction of its maximum value. So typically, so for here, the maximum is V1. So the timing pulse is going to be generated at time that corresponds to K times V1. So with K typically between 0.2 and 0.5, okay? Same thing for the other photon. And that of course is done offline. It's done after you have digitized the signal, and then you can look at the maximum and assign a timing event at this time, basically, at the constant fraction. So that's very simple. So you have two timing events that are associated to each photon, okay? And now the idea is going to be to decide whether, those timing pulses are close enough so that, which would mean that, the two gamma photons come from the same annihilation event, okay? So you have another layer of processing that is because, of course, you may have some differences between T1 and T2, although you have, they come from the same annihilation event, okay? And that can be due to several factors, one of which being the fact that each photon may actually, is going to travel a different distance inside the patient. So of course, those photons are traveling at the speed of light, but if you're talking about 1 meter diameter bore, so detectors placed 1 meter apart, basically, and then you have an annihilation that happens in the left flank of the patient, you can have one photon that is detected right away by the detector that is the closest, and the other photon that has to travel the whole length of the patient, basically. So that is going to lead actually to small timing differences that can be up to 3 nanoseconds for a 1 meter diameter bore. Okay, so when the system decides whether T1 and T2 are close enough, to form a coincidence event or not, it has to account for this potential 3 nanoseconds difference. Okay, and of course all the steps here can introduce some errors by the CFD, the electronics, etc. So you're going to have on top of that another potential source of error in a time pickoff due to the finite timing resolution of the detector, CFD, etc., etc. Okay. So the way to do that is that the PET scanner is actually going to pass those timing pulses to what we call a gate generator. So it's basically just going to create a pulse of longer duration that incorporates these potential sources of difference for each one of those timing pulses. So the pulse have a duration of that is called tau. So this is called the coincidence timing window of the PET scanner, and that's typically 3 to 6 nanoseconds. Okay. So you have T1 and T2. You pass those to a gate generator, and then you create pulses of longer duration. So again, 3 to 6 nanoseconds for most PET scanners. And of course, then you can simply, sum those two signals. And if you have overlap in time between those two signals, it means that those photons are likely to come from the same annihilation events, basically. So that's how it works. So this is a summary here. So you have annihilation that happens. You have 2 gamma photons that are emitted. You have electric pulses that are produced by the combination of the scintillator and the PMTs. You can have a first source of, of offsets here, temporal offset between the two signals due to the differences in traveling distance that can be up to 3 nanoseconds for a whole body PET scanner. Those pulses are passed through CFD. So you have those pulses here that are created, timing pulse. You have, of course, an increased uncertainty here, temporal uncertainty that can be caused by errors in time pickoff. And then to account for all those, you pass your pulses through a gate generator. And then that creates, as we've seen before, pulse of longer duration for both of those timing pulses. And if you have overlap here between the two pulses, then your scanner is going to record a coincidence event. If this pulse here was slightly shifted here, and you would not have overlap, then you wouldn't have a coincidence event that would be recorded by the scanner. Okay, so it's a very simple processing. Okay, so let's move on. So these are the different types of coincidence that can occur. So this is the base case scenario in PET. So this is what we call a true coincidence. So here you have annihilation that happens, 2 gamma photons that are emitted, and then they're activating those 2 detectors. Okay, so here you have your line of coincidence that is going through the site of annihilation, and that is typically the useful data in PET. Okay, so these are the best events, the best types of coincidence events. Okay. Another type of coincidence that we've seen, that we've talked a bit about before, is what we call a scattered coincidence. So here again, you have an annihilation that happens, 2 photons that are emitted, but then you have 1 or both photons that is actually interacting with the patient here and be scattered. So instead of detecting this line of response here between those 2 detectors, due to scattering, you're going to detect this line of response. Okay, so so this line of response is going to activate this detector. So as you can see, that's not good for us because the line of coincidence here is not going through the site of annihilation. Okay, so this coincidence actually carries erroneous spatial information. It's going to reduce the contrast of the PET image, and of course we want to get rid of them, and we need to have correction techniques for those. So I've said before how we can use energy to correct for scatters, but there are some additional corrections that we have to do as well, and that you'll talk about with George on Thursday. So these are the scattered coincidences, random coincidences. So here you have 2 annihilation, completely unrelated, that happen at the same time. And then for some reason, then you have two detectors that are activated at the same time, okay? So for instance, here you have one photon that is absorbed by the table here, the other one that is detected by this crystal here. And in the other case, you have a photon here that goes through both crystals and the other one that is activating this detector. So what's going to happen here is that the line of coincidence here is going to connect those two detectors, okay? And that, of course, has nothing to do with the annihilation events. And we need, again, also to correct for randoms, okay? So a very important correction that we have to do in PET is to correct for random coincidences. And finally, this is the multiple coincidence. So here, instead of having two detectors activated by two or more annihilations, you actually have three detectors that can happen too. And that is typically not saved by the PET scanner because you have no idea where to put the line of coincidence. So those are rejected by the PET scanner, okay? So to understand the contribution of those coincidences on the signal, we can do some simulations. That's a very good thing about PET and nuclear medicine imaging is that we have very sophisticated and accurate simulation tools, so Monte Carlo simulation tools that we can use to simulate an entire PET scanner and an entire distribution of activity, with a geometry that we want. So it could be simple forms like a cylinder, or it could be a whole patient, basically, digitized patient. So this is pretty useful to test configurations, correction methods, etc. So here what I've done is that I've simulated a uniform water cylinder filled with fluorine-18 using one of the simulation tools. So the diameter of the cylinder is about 36 centimeters. So this would typically mimic a patient, basically, a cylinder of water, 36 centimeter diameter. This is the PET camera that was simulated is a Philips Gemini. So it's an older also PET scanner, but it's still useful in simulation. It has scintillators made of GSO. The field of view is 57.6 in the transaxial direction and 18 centimeters in the axial direction. Coincidence resolving time that we've talked about is 8 nanoseconds for this scanner. And we've simulated 60 million coincidence events, okay? So this is the result of the simulation. So this is what we call a sinogram. So it's basically the way we organize the PET data, the raw data in PET, okay? So it's basically an array of generally 3 dimensions that basically is organizing all the line of response. And each pixel of the sinogram is basically showing you the number of coincidences that were detected in this particular line of response, okay? So here you have the distance and the angle, okay? So that's basically indexing all the line of response. So for instance, if you take a row of your sinogram right here, so you change the distance, but you keep the angle. So it's basically going to index all those line of responses. So this one, this one, this one, all the ones that have the same angle, but a different distance. And that's how you move through your sinogram space, okay? So this is the sinogram of all the coincidences that have been detected, okay? So of course you can see the boundaries of your cylinder in the sinogram domain, a lot of signal in this area of the sinogram domain, but also you can see, a lot of signal outside the objects. And that was typically going to correspond to all the unwanted coincidence events that we've talked about before, okay? So one of the good things that we can do if we have simulations is that we know the ground truth and we can separate the signal into its components. So this is what I've done here. So this is a sinogram of all the coincidences I've shown before, true coincidences only. So you can see here, all the signal is located within the boundary of the object, nothing outside. So this is, typical of the true coincidence, the good ones. These are the random coincidences. So it's basically a uniform, background here that is on top of your useful signal, because, it has little to do with the structure of the object that is inside the scanner. It's really uniformly, illuminating your crystals, basically. And this is the sinogram of scattered coincidence. So you can see that it has some spatial information, right? You can see the boundaries of the object here, but you can also see the leaking of the signal here outside the object. And that is typical of the scattering that is deflecting the trajectory of the photon so that it's going out of the object boundaries, basically. Okay. So to give you an idea, also we can compute the respective fractions of those coincidences on the total. So this is what this is showing here. Truths, so the good events, only 36% of the signal. Okay, that means that 64%, all the rest is noise and unwanted data that we're going to have to reject. Okay, so random, scattered, about 30%, multiple 6%. So it's really important in PET to have, especially if you want to have a quantitative image, so an image that has a good estimate of the, amount of activity that is in each pixel. You really need to have accurate correction methods to remove those randoms and scatter coincidences. Okay, and there, people have worked for decades on improving and developing and improving those corrections. Okay, so let's move on now. So now we're going to talk about some basic aspects of the geometry of the PET camera. So this is a view here, a sagittal view of the PET scanner. So you have to imagine that you have rings that are coming in and out of the slide here. And this is your patient, so it's on a table, of course. And of course, as you have injected the radio tracer, you not only have signal within the field of view of the scanner, you also have activity everywhere outside, okay? So what can very well happen is that you're going to have annihilation events here that happen in the feet or in the thorax that are going to produce photons that can interact with your scintillators, okay? And that would typically create a lot of randoms. So one of the important things that the PET scanner has to have is shielding. So it has to be shielded from outside radiation. And this is how the shielding is designed, basically. So it's a cylinder made of lead or tungsten that is placed on each side of the actual field of view, so that many, not all, but many of the photons that are emitted from outside annihilations are going to be stopped by those shields, okay? It's a very important component. Now I'd like to talk about the data acquisition, so the 2D versus 3D mode. So many of the old scanners, such as the HR Plus that I've presented before, could be operated in 2D versus 3D mode, and 3D mode actually, both. So in 2D mode, what can happen is that what's happening is that you have septas, so made of lead, that are going to separate your rings of detectors. Okay, so for the HR Plus, you have 32 rings here. So you're going to have a septa that is separating each one of those rings, so that only the coincidences that are between detectors that are located within the same ring or directly adjacent rings are going to be allowed, basically. So although it's called 2D mode, of course, for each plane here, you're collecting a slice of your patient, and of course you can reconstruct a 3D volume out of that. But the acquisition is 2D because you only accept coincidences that occur between detectors located in the same ring. Okay, can you see my screen? Oops. Can you see my screen?
Yeah, you're in. We see the unmaximized presentation right now.
I'm sorry, something happened. Yes, do you see now?
Yeah.
Okay.
Yeah, you're back to the presenter view.
Okay, so of course, those septas here, so separating each ring, you're going to have, of course, a lot of true coincidences that are going to be blocked by the septas, okay? So that's going to lead to a loss of sensitivity, basically, by the 2D mode, because all these true coincidences here, if they hit with an incidence angle here that is like that, they are going to be absorbed by the septas. Good thing about the 2D mode, though, is that many of the scattered photons are also going to be, rejected by the septas, okay? So if you think about this ring of detector here, all those scatters here that could have contributed to this, plane of detection are going to be blocked by the septas. So typically, you're going to have a lower number of scatters when you use 2D as compared to 3D mode, okay? So this is how the 3D mode is retracted, so is working. So here the septas are retracted. So you're basically going to allow coincidences to happen between any ring of detector. Of course, you're going to have a huge gain in sensitivity because you can detect all those coincidence events here. But the drawback of that is that you're going to have more scatters. So if you remember the plane that we just mentioned for the 2D mode, so this plane right here, of course, true coincidences have to come from within the plane, right? Because they are true coincidences. But all the scatters that come from with this characteristic here are going to be also contributing to your signal for this plane. Okay, so the scatter fraction of the 3D mode, so the number of scatter divided by the total number of coincidence, is going to be higher for 3D as compared to 2D mode. So you're going to have more scatter for more truths, but also more scatters for the 3D mode as compared to the 2D mode. So what about randoms? So randoms, of course, you're going to have more randoms also in the 3D mode, because you have all these randoms here that can contribute to your data as well, while those would be blocked by the septas. Okay, so you're going to have more randoms in 3D as compared to 2D. And something also that is contributing to the increased randoms in 3D mode as compared to 2D mode is the fact that your field of view for randoms is going to be actually a bit larger for 3D mode as compared to the 2D mode, okay? So this is the field of view for true coincidence. It's the same for the 3D mode, because true coincidences have to come from here if they are to be detected by your PET scanner. And this is the field of view for randoms. So you can see that for 3D, you can have photons that are emitted from here and that are not going to be blocked by the shields, and that are going to interact with your scintillators. So you have a larger field of view for randoms as compared to 2D, because here those photons would be blocked by the septas, basically. Okay, so 3D mode, more randoms than the 2D mode. Okay, so sensitivity. So this is 2D mode. So this is a z-axis. Okay, so you only allow coincidences between the same ring or directly adjacent ring, and as a result, this is your what you allow for your sensitivity. So these are the planes of detection for the 2D mode, and this is for the 3D mode. Okay, so in this area here, you allow all those coincidences to happen, all those planes, and of course, you're going to have a much higher sensitivity for 3D as compared to 2D. Okay, so this is how the profile looks like roughly, as a function of axial planes, so the sensitivity for 3D and 2D. So you have a higher sensitivity for 3D mode, of course, as compared to 2D. So this is about 5 to 7 times higher, but you also have a more non-uniform sensitivity profile for 3D mode as a function of the axial planes, which will require some correction in order for your images to look uniform, okay? So this is an example here of 3D versus 2D study. So on the top, you see the 3D image. So this is the heart that we are imaging here, and this is the same patient in a 2D mode. So this data were reconstructed with filter back projection that has a characteristics of giving you streaking artifacts. The higher the noise there is in your data. So you can see that in 3D mode, we have fewer artifacts as compared to the 2D mode, because data have higher signal to noise ratio, basically. So that's, we're going to have a gain in terms of image quality for 3D versus 2D, okay? Overall. So this is a summary. So 3D acquisition improves sensitivity by 5 to 7 times compared to 2D. Main drawbacks of 3D is that increased scatter fraction by a factor of 3, so much more scatters for 3D compared to 2D, more randoms, and also more complex image reconstruction, although nowadays it's no longer an issue because we have very powerful computers that can handle this, so no longer a problem. So now I'd like to quickly talk about the effect of patient size on image quality in PET, and try to link this to the 2D versus 3D mode, keeping in mind that the 3D mode has a higher scatter fraction than the 2D mode in general, okay? So these are some, you're going to understand that. So these are some images taken in patients of different sizes. So 123 pounds on the left, 167 in the middle, and a very large patient here on the right, 266 pounds. So these are FDG scans, and we have injected the same amount of activity per weight of each patient. So, and we have scanned the same duration. Okay, so these are pretty much comparable. So as you can see, the larger your patient is, the worse the image quality is going to be, because you're going to have more scatters. Okay, so the more material you have, the photons have to travel through before they are detected, the more likely they are to scatter, and the more scatter you're going to have if you have a larger patient as compared to a thinner patient. Okay, so you see here that data are noisier because we have rejected more coincidence events than what you would have for those thinner patients. Okay, so keeping this in mind, now let's examine the impact of 2D and 3D modes on the image quality for patients of different sizes. So this is the same patient here, scanned with a BMI of 18, so very thin patient that is scanned with a 2D mode and a 3D mode at the bottom. Okay, so look at these small tumors here that is in the flank of the patient. You can see that with a 3D mode here, you really have a gain in terms of signal to noise ratio, because you have higher contrast, and therefore you can better detect this tumor as compared to what you would have on the 2D mode. And that is a direct result of your improved sensitivities that you get from the 3D mode as compared to the 2D mode. Okay, so here, big gain. This is for a patient with a BMI of 33, so it's already a quite large patient. So here you can see that when you compare those two images, between the 2D and 3D modes, especially focusing on this small lesion here, you can see that the gain of the 3D mode is actually not that visible. It doesn't seem to bring you any gain in terms of your ability to image this tumor and to detect it. Okay, so those are very similar. And that's what's happened, and that is what happens when you have a very large patient. So here, BMI of 50. You can see now that if you focus on this tumor right here, it's almost gone in the 3D mode. So because you have so much scatter, you have rejected so much signal in the 3D mode comparatively to the 2D mode, that here the gain that you have for 3D mode is basically going to vanish as compared to the 2D mode. Okay, so 3D mode is good when you have like thinner patients, but once you have larger patients, scatter becomes such a problem that is going to lead to a degradation of performance, basically. Okay, so that's it for this part. So now we're gonna talk about, to finish, the different factors that affect spatial resolution in PET. So before talking about PET, I'd like to quickly recap how SPECT was working. So as you may recall, of course, in SPECT you have those collimators, scintillators, and that are used to detect only certain photons. So you use those collimators to block many of the photons and only allow some of them to pass, so that you roughly know where they're coming from, and that's how you get the spatial information. So those collimators actually causing a quite complicated properties of the spatial resolution. So actually, the resolution is going to degrade with increasing distance from the detector. Okay, so things that are in this area of the image are going to be have a much worse resolution than if you are closer to the collimators. Okay, because signal coming from here can come from anywhere in this area here, and that effect is smaller as you get closer to your collimators. Okay, so the spatial resolution is going to be very dependent on the distance from the source to the collimator. Okay, and if you have deeper collimators or larger deeper collimators, you're going to have a very different spatial resolution. Okay, so that is quite complicated in SPECT. Spatial resolution. So of course in PET, as you know now, we do not use any LED collimators. We use coincidence detection, or electron nickel emission. So here, the key thing that's going to determine your spatial resolution is going to be the size of the detector elements, okay? So if you have larger detectors, you're going to have a worse spatial resolution than if you have smaller detectors. So for instance, for human scanners, the size of the detectors are typically 4 millimeter for whole body scanners. And for small animal, so for mice and rats, for preclinical studies, the scanners have detector elements that have a size of about 1 millimeter, so much better spatial resolution, okay? Of course, we'd love to have 1 millimeter detectors in human scanners, but that would be extremely expensive to manufacture, and therefore I'm not aware of any of those. So the resolution is really determined by the size of the detector elements. And the good thing also is that the resolution does not change much between the detectors. So if you're here or here, you're roughly going to have the same spatial resolution, okay? So key thing is the size of the detector elements. There are, however, many other factors that are going to contribute to your spatial resolution in PET, and many of them are due to the physics of positron emission and annihilation. So, for instance, the positron range. So, as you may recall, when the positron, when the proton here, the extra proton in the radionuclide is converting to a neutron, you're going to have your neutrino, et cetera, emitted, and also the positron that is going to be emitted. So what's going to happen is that the positron that is emitted here is going to be given some kinetic energy during the emission, okay? And it can only annihilate with an electron when it has lost all of its kinetic energy, okay? So what's going to happen is that the positron here is going to travel in the tissue, is going to collide with electrons, but not annihilate. And each time it's going to lose some of its energy. And once it has almost fully lost its energy, it's going to be able to annihilate with an electron and then produce the 2 gamma photons that we're going to detect, okay? So the distance here, the average distance between the site of emission and the site of annihilation is what we call the positron range. Of course, that is, we don't want to have a positron range because what we really want to know is, where the molecule, the radioactive molecule is inside the patient's body, not, where is the site of annihilation. So this delta here is going to lead to a loss of spatial resolution. So these are some examples here of positron tracks in water that were simulated. So this is for F18. So the source of positron is at the center of this 4 millimeter box here. And you can see here the tracks of the positrons. So positrons are emitted from here, and the end of the track is basically representing the site of annihilation, okay? So you can see that, many of them annihilate, close to the source, but you also have some of them that actually travel, several millimeters before they annihilate with an electron, okay? So that is, positron range is going to be, to depend on the kinetic energy that is given to the positron. And that is going to be different for different positron emitters. So this is the distribution of kinetic energy for the positrons here for different radionuclides. So F18, carbon-11, N13, and O15. So typically the average kinetic energy of the positron is going to be 1/3 or 1/2 of the maximum energy. So for instance, for F18, the maximum energy is 0.6 MeV. The positron on average is going to be given between 0.3 and 0.2 MeV of kinetic energy. So it has to lose all that before it can annihilate. It can annihilate with an electron. So it differs for different radionuclides. So for carbon is more than that. So higher kinetic energy means it's going to travel longer in the tissue, basically, and so on for O15. So these are some positron range, mean positron range here on the right for different radionuclides. As I was saying before, this really depends on the energy that the positrons are given. So this is the maximum positron energy. So you can see that, for instance, for rubidium-82 here, it's positrons have a lot of energy, so 3.3 MeV. So that is going to translate into a very large positron range. Good news though is that for F18, that I said is very important in PET, it's only 0.6 millimeter on average, this positron range. So if you compare that to the 4 millimeter width of the crystal, this is going to be only a small, resolution degradation. Basically, it's going to contribute little to the overall spatial resolution. However, for rubidium-82 here, 6 millimeter positron range compared to 4 millimeter crystals, you can see that this is the dominating effect in terms of spatial resolution. Okay, and you can actually see that when you look at images produced with F18 versus rubidium. So this is a myocardial perfusion imaging study. So it's to image the perfusion of the heart. That was done with rubidium-82 and F18. So F18 on the right and rubidium-82 on the left. And you can see clearly that this image has a much lower spatial resolution than this image. Okay, so the wall here of the heart appears wider than it really is because, although you have radio tracer molecules that are in the wall, the positrons that are emitted are not annihilating inside the wall. They are annihilating around it, and that's why you have a blurring of your image. So you can see that the F18 image has a much thinner apparent wall, and also you can see the right ventricle here that you cannot even distinguish in the rubidium-82 image. Okay, so really a big issue, the positron range for rubidium studies, not so much for F18. So there's another effect also that is going to decrease the spatial resolution in PET, and that's the fact that, as I'm trying to show on this slide, the positron and electron are actually not going to be completely at rest when they annihilate. And that is going to mean that you're going to have some leftover energy and momentum here that is going to be transferred somehow to the photons that are emitted. So what's going to happen is that the two photons that are going to be emitted are not going to be fully collinear. Okay, so there is a small deviation in terms of the angle of those two photons. So it's going to be 180 degrees plus or minus 0.25. Okay, so it's going to oscillate somewhere around this. So you may think that 0.25 degrees is nothing compared to 180. But actually that wouldn't be the case, for instance, in a whole body PET scanner, because here you have, if you have a 1 meter diameter bore, that tiny difference here of 0.25 degrees actually going to lead to up to a 2.5 millimeter positional uncertainty. Okay, so this is what is shown here. So if you had fully collinear photons, you would detect this line of response here. But because you have non-collinear photons, you're going to detect, this line of response here, because you have a deviation in the trajectory of your photons. And that difference here between the recorded coincidence and the one that should have been detected if the photons were fully collinear is going to be about 2.5 millimeter, difference. There's going to be 2.5 millimeter. So of course, this effect is going to be more important for larger diameter scanners. Okay, so if you think now of a brain scanner, so here, let's say for a 30 centimeter diameter bore, the same level of non-collinearity in the photons is only going to lead to 0.6 millimeter on average positional uncertainty. Okay, so the same level of non-collinearity is basically creating, has a worse impact on a whole body PET scan than on a brain scanner, basically. So that is, positron range and photon non-collinearity. There is very little you can do about that. So you can always reduce the size of crystals, improve them, but to have better resolution. But for positron range and non-collinearity, there is not much you can do. So those are always going to fundamentally limit the spatial resolution that you can obtain with PET. Okay, that wasn't the case for SPECT, by the way. For SPECT, you don't have those physical effects at play. So here, if you have very good collimators, very good detectors, you can have a very high resolution. For PET, you're always going to have fundamental limits that are due to those two effects, due to the physics. So lastly, I think so there is another effect also I want to talk about that can lead to a degradation of spatial resolution. That is what we call intercrystal scattering. So this is a case where, the photons here that are emitted are actually not going to be absorbed right away by the scintillators that they hit. They're actually going to undergo Compton scattering, for instance, and then they're going to be absorbed by the neighboring crystal, okay? So that is what we call intercrystal scattering, because you have, like photons that travel between crystals, and that, of course, will lead to a spatial resolution degradation. So instead of detecting, this line of response, you're going to detect this line of response, okay? So of course you wanna minimize this by, having high Z scintillators so that you make sure that photons are stopped right away, when they hit the crystal and don't scatter in neighboring crystals, okay? So that is intercrystal scattering. And finally, this is the depth of interaction effect. So this is the one that's going to create a spatially dependent spatial resolution in PET imaging, okay? So this is how it works. So let's say you have this configuration here. So you have a photon here that's hitting one of those crystals with a 90-degree angle. That's going to be the ideal case, okay? Because here you will have your incidence point that is going to be in the same crystal as the interaction point, okay? So this detector here would be activated by this photon. So that is what we want to have, of course. However, if you go towards the edges of the field of view, this is what can very well happen. So, photons have to travel a certain distance in the crystal on average before they are absorbed. And that is what's happening here. So because photons have to travel through the crystals, through, certain amount of material before they are absorbed, when they hit the crystals with a certain angle, they will actually be, not detected in the right crystal. So this is the incidence point here that is located in this crystal, and the interaction point is actually going to be located in the neighboring crystal, okay? So that is going to lead to a positioning error towards the edges of the field of view. And the further away you go from the center, so the more oblique your photons are going to hit the crystals, the worse this effect is going to be. And that is what is going to create a spatially dependent resolution in PET. So the resolution is degrading as the radial distance increases. So the radial distance is the distance between the center and the edge of the field of view, basically. So for instance, for the HR plus that we've talked about before, the resolution at the center, so right here, is about 4.5 millimeter. 6 millimeter at 10 centimeter of center, and 8 millimeter at 20 centimeter of center. Okay, so it's a pretty large, degradation also of the spatial resolution that we have across the field of view. That is due to the depth of interaction effects. Okay. So that's a summary here. So spatial resolution, as we've seen in PET, is primarily determined by the physics of positron decay and annihilation. So effects such as the positron range and non-collinearity. So there is not much you can do about those. You can model the uncertainty that they are causing in your image to kind of, compensate their effects, but that is never going to be enough to fully, correct these effects. So they are going to really impose a limit on your spatial resolution that there is nothing you can do about, pretty much. Detector size is a very important one. So the smaller the detector, the better the spatial resolution. Detector material. So this is to minimize the depth of interaction and the intercrystal scattering. So the higher Z, the lower these effects are going to contribute to the spatial resolution, and the system geometry, so due to the depth of interaction effects, okay? So that's all I have for today. Do you have any question?